Welcome to Thermal Engineering Concept and Principle. This is Professor Ali Tarra. What do you know about vertical heat exchangers and their philosophy of operation with geothermal heat pumps? We mean here the operation of the borehole geothermal heat exchanger. To know that, come with me to go through details of the present episode. Welcome, my friends and colleagues, to introduce the aspect of thermal design for the boreholes in a geothermal heat pump. In this episode, I will introduce the characteristic of a borehole heat exchanger and its installation in the ground, accompanied by its main components to construct a heat exchanger that is called borehole type, which is a vertical heat exchanger. In this part, I will cover the construction of the heat pump itself and the borehole and how can we estimate the depth of the U-tube in the ground, which is related to the properties of the geological aspect for the ground and the thermal properties of the grout or filling that is surrounding the U-tube in the ground. Thank you for continuous support and let us keep on this series of videos in this field, which is the renewable energy source called geothermal energy. The objectives of the present video covers practical application of the geothermal heat pump, which uses a vertical W tube. And we will pass through the comparison between the utilization of the single and W tube heat exchanger and see how the performance can be changed with these types. And also we will compare the present model which will be presented in this episode with other available correlations, although they are just a limited number of these correlations, but it's useful to compare it with these correlations as well. And finally, we will arrive to the closure of the present episode. We take an industrial case study where a geothermal heat pump is used and it utilizes a direct or DX heat exchanger which acts as a condenser heat exchanger, geothermal type, and we have Freon R410A refrigerant, which is circulated in this system with a condensation heat transfer coefficient of 3000 watt per meter square degree centigrade is used as a typical value. We will apply a double U-tube made of copper, and both the descending and ascending sides of the tube are having the same diameter with different geometries as shown in this table, with WF represents the tube wall factor, which can be obtained by dividing the outside diameter by the thickness of the tube, and we have T is the thickness of the tube, of course. And let us find the performance of the W tube for these geometries with a range of thermal conductivity of the grout material ranged between 0.73 watt per meter Kelvin up to 1.9 watt per meter Kelvin, as shown in the table, and these materials are well known to be utilized in this type of heat exchangers, and some of them are mixture between different materials such as bentonite and 30% quartz. So it's a range of these materials can be used just to improve the thermal conductivity of the crude material, which is reflected on the performance of the tube itself. To compare the Borehole Thermal Design, and we will focus on the thermal resistance of the tube. For example, here we have geometry factor SP divided by dB equal to 0.34 up to 0.56, and these values of SP divided by dBor, which is representing the geometry factor, are obtained for a constant borehole diameter. In this figure, we may see that all these values, regardless of the geometry factor, behave on the same manner. We have a maximum at 0.73, and the minimum will arrive at the value of 1.9. And as we increase the geometry factor from 0.34 to 0.56, the thermal resistance is reduced by tremendous value, and of course that will be reflected on the heat loading of the heat exchanger and the thermal performance of the heat pump itself. And the lower value was obtained for geometry factor equal to 0.56 because in this case we have a constant borehole diameter, but the distance between these two legs of the tube are increased, and in that way we are minimizing the distance between the borehole surface, external surface, and the surface of the tube, and the distance is reduced, therefore the thermal resistance will be reduced as well. We have the same behavior when we have WF equal 12.5, and again here the thermal resistance are higher than the previous one, and again we have the same behavior from maximum value at 0.73, which corresponds to around 0.3, down to 0.16 or the same thermal conductivity and is reduced to a value of around 0.12 for the geometry factor of 0.29 and it's reduced to a minimum for the geometry factor of 0.59 at a value almost correspond to 0.06 and we can see the difference almost double. Now, let us see the effect of tube spacing on the thermal performance. For example, here we have WF equal 14.29 for different values of SP range between 2D naught up to 3D naught for both geometries of the single tube and double U tube as compared here in this figure. And the single tube at the same SP, when it is compared to the double tube, usually the single tube has a higher value than that of the double tube. For example, if we use a form that is eta equal r bore when we have 2D naught, SP equal to 2D naught minus R and where we have SP equal to 3D naught divided by R sub B where we have SP equal to 2D naught. Here for this geometry the lower tube spacing 2D naught exhibited a higher thermal resistance than that of the 3D naught in the range of 22 to 24% for the single U tube and it fell in the range of 32 to 34% for the double U tube case where we have the same variation of SP between 2D naught and 3D naught. Again, if we compare the borehole resistance for the single and the double U tube as represented by zeta, we have the value of zeta fell in the range between 14 to 16% and 25 to 27% predicted as the tube spacing of 2D naught and 3D naught respectively. And that means usually we have the enhancement or the performance or the different depend on the SP value. And this is the case for the WF equal to 14.29. Of course, we have the single tube at SP equal to D naught has the higher value and approaches around 0.3 at 0.73 watt per meter Kelvin and falls down to around 0.14 for thermal conductivity of the root corresponding to 1.9 and the lower value was for the double U tube for SP equal to 3D naught and here almost is double as we can see from this figure. And if we talk about 12 WF equals 12.5, we have the same variation that is usually when SP equal to D naught is higher than that of 3D naught for both geometries, the single and double U tube. And at the same time, we have zeta is having the same values. I mean, we have the single U tube is higher than the double U-tube for the borehole thermal resistance. And here we have eta for this geometry is range between 18 and 19% for the single U-tube, and it is range between 22 to 23% for the double U-tube when we have the tube spacing was 2D naught and 3D naught respectively. At the same time, we have zeta for this geometry fell in the range between 10 to 11% and 15 to 16% for the tube spacing 2D naught and 3D naught. Of course, these values depend on the tube spacing. I mean, for the borehole resistance for both tubes, single and double U-tube. And wherever we have the tubes are close to the boundary of the borehole, then we will get the lower value of borehole thermal resistance, and usually the single U-tube showed higher borehole thermal resistance than that of the double U-tube. Let us compare what we have in the present video and the present correlation with the available correlations. Of course, there are not too many correlations available in the open literature for the W-tube, but we may compare the present model with two of them, that is Schonder and Beck, and the other is the Koenig correlation. Both of them represent the higher and lower values, of course, although the higher value in this model is showed by the present work or the present correlation, but again, it's very close to Schonder. And we have to mention here that Schonder and Beck correlation doesn't depend on the borehole diameter and the spacing between the tubes. But the other correlations, I mean the present model and the Koenig equation, represents variation and showed its influence by the change of these values of SP and DB. And all of these correlations showed the same behavior and the trend of these thermal resistances, and Koenig model showed a very low values when we compare them with the present and Schonder and Beck correlation. Here we have the WF equal to 12.5, where we have the DB equal 65 millimeter. Again, we have here Schonder and the present model showed the higher value, and they are very close to each other, and the minimum value was obtained by Koenig equation, and the present correlation and Koenig correlation showed variation depending on the value of a geometry factor, which is SP divided by D bore. For example, at 0.29, we have the higher value of the thermal resistance, where the a lower value was obtained at SP divided by D bar equals to 0.48, which is represented by the blue line, and these values show that the higher the thermal conductivity of the grout material, the lower thermal resistance, which is reflected, of course, on the size of the uh, tube and its depth. Therefore, we have to select an accurate correlation to predict the thermal design of such heat exchangers, as can be seen here that, for example, at for the present model and shown there for geometry factor of 0.29, almost the thermal conductivity at thermal conductivity of 0.73, the thermal resistance around to 0.28. When we compare at the same value with the Koenig equation, almost is zero point 0.1. And we can see here that the difference will be huge in the thermal design for the depth and the surface area of the heat exchanger, as it's varied from a little value at 0.1 up to a high value at 0.3 for the thermal resistance. And again, if we increase the thermal conductivity to 1.9, then we will get the best performance for all of these correlations and predict a lower value for the depth or the length of the heat exchanger itself. Then we have arrived to the closure of the present model. We passed through the thermal design, the W tube, and compared to that of the single U-tube heat exchanger. Of course, we have compared the present model for the W tube with the available correlations. We have some valuable resources in, presented in a link in the description box. You may make use of them. And thank you for your support. And I hope to see your comments at the box below the video. And at the same time, I would like to hear your opinion about what we are doing in this series for the geothermal and renewable energy sources. Please share the information available in this episode with your friends, colleagues, and subscribe and like what we are doing, because that will give us a great motivation to do more and to present more of these videos, which are free of charge. And thank you so much, and I will see you in the next episode. Bye.